Oh, it's still not working. Still
Go to the left corner of your PowerPoint. At the bottom, there should be a couple arrows in the corner.
No, it doesn't show. No, it's not showing. It's not there. If
it doesn't show it.
No, it doesn't show that. Yeah, I know what you mean. I used to have that, but it's not showing now. So I can't change the slide. Oh, what's going on here? Can you change the slide for me?
Qian, Benedicta can share the PowerPoint from her screen.
Right, that's good. If she can change the slide for me, and I tell her when to change the slides. Is that okay? Okay, good. Yeah, okay. Right. Should we restart now? Hello?
Yeah, it's now on Benedicta's screen, so you can start now, Qian. Thanks.
Okay. Right. Sorry for the problem. Now let's carry on. Benedict, next slide, please. Yeah, can we have next slide, please?
Does it not go to the next slide?
No, no, the one before, please. Okay.
Yeah, Benedicta was having the same trouble as you, Qian.
At least on her screen, I can see the you know, the buttons underneath, so you can press to change, go forward or backwards. But I don't have that on my screen. Anyway, let's carry on. Sorry about this problem. Yes, this is today's outline. I'm going to talk about the potential role of ammonia in future energy mix. I will then give an overview of the existing ammonia value chain from production, supply, and distribution to utilization, and a review of the latest developments in ammonia combustion technologies. I will discuss the challenges and opportunities of using ammonia fuel, the importance of policies in widespread deployment of clean ammonia fuel, and finish with key messages from my study. If you have any questions, please type your questions in the question box provided, and I will try to answer them at the end of my talk. Next slide, please, Benedicta. Yeah, the first message, thank you. Before I start, I'd like to describe the definition of 3 types of ammonia often referred to throughout my presentation. Brown ammonia is unabated ammonia produced using fossil fuels so it has large carbon footprint. Brown ammonia is also called gray ammonia by some people, or conventional ammonia. Blue ammonia is produced from fossil fuel with carbon capture, so it has a low carbon footprint. The green ammonia is synthesized using water electrolysis and powered by renewable energy, so its production is carbon-free. Next slide, please. Next, please. So why using ammonia? Ammonia can be easily liquefied under mild conditions, either by compressing to 10 times atmospheric pressure or cooling to -30 degrees C, which are similar properties to liquefied natural gas. This means that ammonia can be stored in liquid phase in a simple, inexpensive pressure vessel and be distributed by various means such as railways, ships, pipelines, and storage depots. Liquid ammonia has an energy density of about 3 kilowatt-hour per liter, which is lower than but comparable to fossil fuels, as you can see from the left figure of this slide. Ammonia has a large weight fraction of hydrogen and can be catalytically decomposed into hydrogen and nitrogen gases, as shown on the right of the slides. The transport and long-term storage of ammonia is much cheaper than for hydrogen. This makes ammonia an attractive candidate as a hydrogen carrier, a medium for energy storage, and a fuel. Ammonia is increasingly recognized by many people as an enabler of a hydrogen economy. The MICE study focuses on the ammonia fuel use. Next slide, please. Similar to hydrogen, ammonia is a carbon-free fuel. Burning ammonia produces mainly water and nitrogen. Replacing fossil fuels with low-carbon ammonia in existing combustion systems can reduce life cycle greenhouse gas emissions. For coal power generation, substituting coal with clean ammonia could reduce CO2 emissions by 80 to 95%. This is important for countries with young coal fleet and all with limited low-carbon dispatchable resources, especially in East and Southeast Asia. For power plants where carbon capture is not a viable option due to a lack of storage sites, for example, or because the plant has limited remaining life, ammonia combustion is one way to reduce CO2 emissions. Co-firing ammonia can reduce the risk of existing plants becoming stranded assets by allowing them to continue operating even when climate regulations are tightened. Therefore, ammonia could play an important role in a clean energy transition. Next slide, please. And the next one. There are 3 well-established technical routes for ammonia production. They are natural gas SMR, coal gasification, and the water electrolysis-based Haber-Bosch process. Electrolysis provides a technical route for green ammonia production if renewable energy is available to power the production process. Blue ammonia can be produced by combining a fossil fuel-based process with a carbon capture device. Next, please. Ammonia has been widely used for over a century, So its production, transport, and distribution in infrastructure already exists worldwide. Around 180 million tons of ammonia is produced every year, with natural gas SMR accounting for over 70% of global ammonia production. Coal gasification-based process, which is mainly found in China, produces around 26% of ammonia. Fossil fuel-based ammonia production today is generally unabated. Only less than 1% of ammonia is made using electrolysis. Currently, there have been a number of green and or blue ammonia production projects being announced or under development worldwide in Europe, in the Gulf states, Australia, and America. In general, the scale of green ammonia production is small due to the limitation of the average size of wind and solar power plants. However, there are very large projects being announced recently. For example, the $5 billion projects being developed in Saudi Arabia. When it completed in 2025, it will be powered by 4 gigawatts solar and wind power plants and produce 1.2 million tons per year of green ammonia. And there is another one in the early stage of development in Oman, which will be developed in different phases. It plans to install 25 megawatts of solar and wind power generating capacity, and have the potential to produce up to 10 million tons of green ammonia every year. Ammonia is mainly used as a fertilizer, but it also has applications in many other sectors, such as chemical, food processing, pharmaceutical, and textile industry. Next, please. And next. There are several power technologies that work well with ammonia as a fuel. Ammonia can be directly burnt with minor modifications in external combustion engines or ICE, gas turbines, coal boilers, or be fed into a fuel cell to produce electricity. It is challenging to burn ammonia in existing combustion systems due to the lower energy content and the reactivity of ammonia. However, studies reveal that technical challenges of burning ammonia and the resultant emissions of nitrous oxide and nitrogen oxides can be tackled using existing technologies. Next, please. There are several extensive R&D to develop ammonia co-firing and pure ammonia combustion technologies for power generation are being carried out, and significant progress have been made in Japan. Small-scale ammonia coal co-firing has been successfully demonstrated at existing power plant. Work is now ongoing to demonstrate 20% ammonia coal co-firing at a 1,000 megawatts commercial coal power generating unit in 2024. The ammonia single-fuel burner that can burn over 50% of ammonia is in development and scheduled to be verified for 2 different types of coal boilers by 2028. Developments of ammonia coal-fired power generation technologies have also been reported in South Korea and China. Ammonia-fired gas turbines for power generation are in development as well and could be commercialized in 2025. Next, please. Ammonia combustion technologies are also developing fast in marine shipping. Ammonia-fueled engines, the designs of ammonia-propelled ships and the ammonia-fed fuel cells for ships are being developed in Europe, Japan, and other countries. The first commercial vessel fueled by ammonia can be expected to be launched in 2024-25. Many more projects are on the way to convert existing vessels to run on ammonia. Next, please. Despite the extensive R&D activity and some ongoing projects to convert existing road transport vehicles to ammonia diesel dual fuel, the future of ammonia fuel in the car market is uncertain because battery-powered electric vehicles are currently more economical and are already an established technology. Next, please. And again. A major barrier to use clean ammonia fuel is cost. There have been several assessments of the cost of ammonia, and the results all indicate that the cost of green ammonia is more than double than that of brown ammonia, and it is likely to remain high for the coming years. Due to the added cost of carbon capture system, the cost of blue ammonia is around 25% higher than that of brown ammonia. The increase in blue ammonia production cost can be largely offset by, for instance, emission charges, making the blue ammonia is a potential viable choice for low carbon fuel. This figure here shows the results from a recent IEA study, and it compares the cost and the carbon intensity of ammonia produced by different routes. Next slide, please. Expanding ammonia use as a fuel could increase demand substantially. As an indication, if all coal-fired power plants in Japan were to coal-fire 20% ammonia, then 20 million tons ammonia a year would be required for coal-firing in Japan alone. A recent estimate by commodity experts found that the potential use of ammonia as an energy source could create a 1 billion ton per year market. This volume is many times more than today's global total production capacity, and this would require a massive scale-up of ammonia production capacity and the distribution network. Importantly, the current renewable power generation capacity is insufficient to supply the grid while also supporting the production of green ammonia. This means the cost and the availability of green ammonia may limit its use as a clean fuel. Extensive R&D is being carried out to improve existing technology and develop novel green ammonia production technologies with high efficiency and reduced cost. In the meantime, blue ammonia could enable the earliest adoption of low carbon fuel and facilitate the transition towards increased use of green ammonia in the longer term. Therefore, implementing carbon capture to fossil-based ammonia production is critical to take the large-scale clean ammonia utilization off the ground. It is essential to start now planning and investing in building new ammonia production capacity with CCS and retrofitting the carbon capture devices to existing ammonia plants in order to meet the projected increase in demand for low carbon ammonia. More work is also needed to reduce the cost of clean ammonia. Next, please. Successful uptake of ammonia fuel use depends on the development of supportive policies, incentives, national and corporate greenhouse gas emission reduction targets, and requires the establishment of efficient safety legislation for extending ammonia use as a fuel in various sectors. Several countries have recently produced hydrogen development strategies which have motivated extensive R&D in using ammonia as an enabler of the hydrogen economy. Japan in particular endorses the development of a hydrogen economy to achieve carbon neutrality by 2050. As an island country with limited carbon hydro resources, Japan relies on imports for almost all its oil, gas, and coal as primary energy supply. Japan's energy policy is based on fundamental principles of safety, energy security, economic efficiency, and environmental suitability, which recognizes the importance of coal in secure and reliable primary energy supply. In its most recent strategic energy plan, coal's role in power generation beyond 2030 is clearly defined. The plan sets target to increase energy efficiency of coal power plants and co-firing 20% ammonia with coal by 2030 to achieve decarbonization goals of coal power generation. Japanese government promotes ammonia fuel use in thermal power plants and shipping by setting up a hydrogen and ammonia related technology roadmap and prioritizing ammonia fuel in its green growth strategy. As a result, Japan leads the R&D and the deployment of ammonia fuel for power generation. Japan's power generator, JERA, plans to co-fire ammonia at its thermal power plants in around 2030 as one approach to achieve zero emission by 2050. Plans to commercialize ammonia firing gas turbine by 2025 for power generation have also been announced by Japanese companies. Supportive policies such as emission charges and the tax credits, incentives, and some financial support are also needed to help overcome the high cost of clean ammonia and to attract and de-risk investment. Next, please. Ammonia is a toxic gas. Prolonged exposure to high concentrations of it can be detrimental to human health. The health and the safety aspects of extending ammonia use in the transport, energy, and other sectors should be evaluated, and the new protocols and the regulations for safe handling and the use of ammonia needs to be established. The impact of ammonia use as a fuel on air quality and the environment require further analysis. Limiting values of nitrous oxide and the NOx emissions, similar to those for fossil fuel combustion, should be established and applied to ammonia combustion. Next, please. While there are challenges to extending the use of ammonia as a fuel, there are also opportunities. The opportunity for investors as the market is potentially huge. Ammonia fuel use also generates new business in the clean energy field. It could create jobs and stimulate economic growth. But most of all, ammonia fuel use provides an alternative approach to decarbonize emission-heavy sectors. Analysis by scientists around the world have shown that replacing fossil fuels with clean ammonia for power generation, transport, and in other sectors can lead to life cycle CO2 emission reductions. Next, please. So the key messages are: ammonia has the potential to become a key element of a net zero energy mix, especially in energy-intensive sectors such as power generation, transport, and some industrial processes. Replacing fossil fuels with green or blue ammonia in combustion systems can result in life cycle CO2 reductions. Blue ammonia can offer a quicker and cheaper start for a gradual transition to green ammonia utilization. Rapid adoption of carbon capture to fossil-based ammonia production is essential to an early large-scale uptake of ammonia fuel use. Ammonia combustion technologies are under development and can be expected to be commercialized within 5 to 10 years. It is likely that power generation and marine transport will be among the first to deploy ammonia fuel to decarbonize the sector. And the supportive policies are key to successful deployment of ammonia fuel use. This is the end of my talk. Thank you for your attention. Now let's see if we have any questions. Okay. Yeah, we got some questions here. Right, and the first question, you talk about the cost which shows the green ammonia is more expensive than blue ammonia. But what does clean ammonia compares to fossil fuel, such as natural gas and oil? Well, there is a recent analysis of conventional fuel, comparison of conventional fuel with not clean ammonia, but the brown ammonia. Because the energy content of ammonia is lower, so the comparison was made based on the energy content. So they convert the cost of ammonia to a ton of equivalent to very low sulfur fuel oil for marine transport. Because the recent increase in natural gas prices, so the ammonia price has more than doubled earlier this year compared to last year. And this price is compared for the Northwest Europe. The natural gas, the ammonia for a ton of equivalent fuel oil is I can't remember the number. It's more than twice. Yeah, I think it's more than twice of liquid natural gas, and about 3.7 times of fuel oil. When you put the emission charges and the taxes added by the Europe to the fossil fuels, then because ammonia is carbon-free, it is carbon-free fuel, so it doesn't have to pay the emission charges. So that price compares like it's 1.7. The ammonia is 1.7 times of liquid natural gas, and about 2.4 times of fuel oil, if I remember correctly. So it is more expensive. But if you have carbon charging and other policies in place, that can largely offset the increased cost of ammonia. Then, right, let's see the next question. Coal-fired ammonia may be an alternative approach to carbonized coal power generation. What is the impact of ammonia coal-firing on the cost of electricity? Well, there have been a few studies evaluating the increased cost of using ammonia to the cost of electricity. The IEA has done case studies last year, I think, the cost of electricity increased by using green ammonia and blue ammonia. And it depends on the country, on where the ammonia is produced, and the power plants, existing power plants conditions, and the policies in the country, many factors. But for example, if Japan is to import the blue ammonia from the Gulf state, because Japan has carbon emissions in place, so the increased cost will be largely offset by the supportive policy. if the ammonia, the same ammonia is imported to Indonesia, then the increase cost, increase in cost will be larger, because first the power plant efficiency is lower in Indonesia, and secondly, it doesn't have any carbon emission charges in the country, so you don't have any supportive policy to offset the increase in cost. And there is another study done by Japanese researchers. They have a detailed analysis of importing blue ammonia from UAE, and yeah, they found the if the CO2 captured from the blue ammonia production can be sold for EOR, then the price could be further reduced. So if the blue ammonia import to Japan, and with 20% co-firing of blue ammonia in the coal power plants, the increase in cost of electricity could be controlled under 2 US cents per kilowatt hour. Right. Let's see. Here's another question. Given the challenges of establishing ammonia as a viable zero carbon fuel, does hydrogen offer a more attractive option? Well, hydrogen technology is being developed to be applied in like steel making, some industry, which in some sectors like the long haul road transport, the hydrogen production, hydrogen combustion technologies are more development, are more advanced, more in a relatively matured, advanced development stage than ammonia. So in those sectors, ammonia use is uncertain because it's not competitive to the hydrogen technology. Please, can you show how to produce green ammonia? Well, green ammonia is produced by water electrolysis. You basically, supply the power to the electrolyzer, which is split water into hydrogen and oxygen molecules. That's how you produce the green ammonia. Right. Another question. Next question is, ammonia co-firing at existing coal-fired boilers will be applied to Japan only. Please advise. No, it actually in South Korea they have set target to co-fire 3%. Or 3% of electricity, I can't remember exactly. 3% of electricity is produced from ammonia combustion. Yeah, they have a target to co-fire ammonia with coal in coal-fired power plants as one approach to meet its carbon emission reduction target. And also in China, they have done the ammonia co-firing technology development work, and they have just announced, they have achieved some success in that. But I don't know if they have any target to co-fire ammonia at its power plants. And I know other countries like Indonesia are also interested in ammonia co-firing technology for power generation. And I think they're working with Japanese engineers to do early feasibility studies now to implement this technology later. Let's see. How do NOx emissions compare against natural gas or coal-fired power plant? I don't know, what do you mean? How do NOx emissions compare against natural gas or coal-fired plant? You mean for coal-fired ammonia or just pure gas or coal-fired power plants? I know for coal-fired power plants, the technologies do have advanced now. In China, they have this program to upgrade their NOx control systems, which can bring the NOx emission down to the level comparable to gas-fired power plants. So this is a widespread in application in China. It's existing technology. Right, that's all. Well, if you have any more questions, just email me. I will just answer back, by email. And thank you very much for your time.
Thanks, Qian. The presentation will be available on our website later today, and the report will be published this summer. Thank you all for joining, and goodbye.